continuing applications of derivatives, we're going to talk about increasing and decreasing functions. So, increasing and decreasing, those definitions have nothing to do with calculus directly. We're going to use calculus to talk about them. Yeah, no. And once they get around you, they just seem to be, it happens to me up here all the time. People think I'm having a fit or something because I'm swatting at things. Um, but increasing and decreasing has nothing to do with calculus in itself. So a function is increasing on an interval if for any two numbers, x1 and x2 in the interval, if x2 is bigger than x1, then f of x2 is bigger than f of x1. So as you move to the right, if the graph has moved up, well, the function was increasing on that interval. And then the opposite for decreasing. So increasing and decreasing are not defined by calculus. I had an argument with a lady at the AP reading one year about this, where I was like, because of what we're about to learn, she's like, no, this is how it's defined. I'm like, no, it's not a calculus thing. So I always try to impress, if a teacher can miss that, then I try to impress it on students that increasing and decreasing, it's just, is the function going up as it goes to the right? Is the function going down as it going to the right? That's the definition of increasing and decreasing. Now, how do we test that? And this is the part that the teacher I was having an argument with where she was incorrect about this. So if f is a function that's continuous on the closed interval from a to b and differentiable on the open interval from a to b, which by the way sounds a lot like the mean value theorem, right?
Sorry.
No, it's okay. If f prime of x is greater than 0 for all x in the open interval from a to b, then f is increasing on the closed interval from a to b. And if you think about that for just a second, if I have a function that is increasing on an interval, what's true about all of the tangent lines? Well, any place you draw a tangent line to this, the slope is positive. So what this says is, if we can find an interval where f prime is greater than 0, then f is increasing on that interval. And then conversely, if f prime of x is less than 0 for all x in the open interval from a to b, then f is decreasing on the closed interval from a to b. And if f prime of x is equal to 0 for all x in ab, then f is constant on the closed interval from a to b. One thing to point out is increasing and decreasing is on an interval. Although sometimes textbooks will say things like whether a function is increasing or decreasing at a point, we really define it on an interval. Okay? So like sometimes on this, someone will go, okay, at this point, the function is increasing. And what you're really saying when you're saying that, you're just saying on an interval that includes that point, this function is increasing. Okay? So, for example, let's find the intervals on which this cubic function is increasing. So we'll start by taking the derivative. That's 3x squared minus 2. And we'll set that equal to 0 to start with. So that's going to be 3x squared is equal to 2. So x squared is equal to 2/3. So x is equal to plus or minus the square root of 2/3. So each of those is and I'm trying to remember now. Have we talked about critical points?
Yeah.
Okay. Sorry, I get confused because I do A, B, and B, C, and switching back and forth, I have trouble remembering sometimes. So those are critical points. Remember, a critical point is a point where our function can change direction. So what I typically do is draw a number line and put the two places where, I'll get it, where f prime of x is equal to 0. We don't want any. How'd it go?
Okay for the most part.
Okay, that's fair. So I'll put those on a number line like this, and then what I do is I look at what happens to f prime. Well, f prime is 0 here and here. And then all I need to do is test any point in these. I've got three intervals now. I've got, the interval from 0 down to negative infinity, from 0 up to positive infinity, and I'm sorry, from negative square root of 2 over 3 down to negative infinity, from square root of 2 over 3 to positive infinity, and then in between. All I need to do is check any value in one of those intervals to decide whether f prime is positive, negative, or 0 throughout that interval. So like if I start at 0, substituting into f prime at 0 is negative 2. So that means that f prime here is always going to be less than 0. The square root of 2/3, I don't know how much it is. I just know it's less than 1, right? So if I test what happens at x is 1, back in my derivative, f prime at 1 is 1. So throughout this entire interval, f prime is going to be greater than 0. And then the same for negative 1. Substituting it in, I get that f prime is still 1. So here, f prime is greater than 0. So the intervals on which f is increasing, so f of x is increasing on the interval from negative infinity to negative square root of 2/3, and it's going to be closed at the negative square root of 2/3. The only reason it's open at negative infinity is because negative infinity is not a number, so I can't, put a square bracket there. And on the closed on the left, square root of 2/3 to positive infinity. Now, what's likely to happen on AP exam if they ask you a question like this, they're going to ask you to justify your answer. And at one point, they took what they called a sign chart like this as justification. They no longer do, haven't for years. What they want for a justification is just a short sentence, because f prime of x is greater than 0 on the open interval from negative infinity to negative square root of 2/3, and the open interval from the square root of 2/3 to infinity. All right. So The first derivative test for critical points. Notice this is not the first derivative test. This is the test for increasing and decreasing functions. Does it use the first derivative? Yes, it does, but it's not the first derivative test. Students sometimes get this all confused. The first derivative test for critical points says let f be a differentiable function and c be a critical point of f. Remember a critical point? F prime has to be equal to 0 or f prime has to not exist at that point. If f prime of x changes from positive to negative at x equals c, then f of c is a local maximum. Because when we change from f prime as positive to f prime as negative, we're changing from f as increasing to f as decreasing. And if f prime of x changes from negative to positive at x equals c, then f of c is a local minimum. And then there's always the third possibility that f prime of x does not change sign at x equals c, then f of c is neither a local minimum nor a local maximum. All right, so let's find the critical points and analyze whether each is a local minimum, local maximum, or neither, and we'll justify our answers, okay? Justifying your answers, again, that's not in the book a lot of times, but it's a good habit to get into. Now, if it's a long assignment and it gets to the place where you're like, okay, I have to stop doing this, I get it, okay? But f prime of x is 3x squared minus 27. I always make myself first look at, is there any place where the derivative is undefined? No, right? There's no problems here. But if you'll think about the undefined first and kind of make yourself do that, what happens is a lot of times students rush to, I'm going to set the derivative equal to 0 because I want to find the zeros, that they'll forget to check for the undefined part. So I'll set this equal to 0. So that means that 3x squared is equal to 27. Divide x squared is equal to 9. So x is equal to plus or minus 3. The analysis is very much like what we just did a moment ago. I think a number line is helpful. It's not sufficient as justification, but it is helpful. So these are x values, and then up here I'm going to have f prime of x. So at -3 and at 3, f prime is equal to 0. Then again, I'm just going to check any value in each of these 3 intervals to decide whether f prime is positive or f prime is negative. So if I pick a value bigger than 3, I'm going to pick 10 because it's easy to work with. 3 times 10 squared is 300 minus 27. I don't care about the value, I just care about its sign. That's definitely positive. In between -3 and 3, 0 is an easy test point. Substitute it in, I find that f prime is -27, so here f prime is less than 0. And here I'll pick -10. I get exactly the same thing I got from +10. F prime is greater than 0. So at x is -3, f prime changes from positive to negative. So f of -3 is a local maximum because, and let's look back at what this says, it has to be a differentiable function, which means it's continuous also, because f is differentiable and f prime changes from positive to negative at x is equal to -3. Then f of 3, well, here f prime changes from negative to positive, so f of 3 is a local minimum because, again, f is differentiable and f prime changes from negative to positive at x equals 3. Oh, and just a real quick, by the way, on this one. 3x squared minus 27, that's an upper-facing parabola, right? And we know that the roots are at -3 and 3. You know that f prime is going to look something like that, right? When you have a problem like that, you don't need to spend this much time finding the interval, finding test points and all that. You're like, I know what this looks like. Okay? So on the AP exam, you almost never get quadratics and the like. Quadratics work nicely here because they're easy to work with. All right, let's look at this. Analyze the critical points of f of x is 1/3 x cubed minus x squared plus x. All right, so f prime of x is equal to x squared minus 2x plus 1. Again, are there any places where the derivative doesn't exist? No. So I'll find where this is equal to 0. And that's going to be what? X minus 1 times x minus 1? So there's only one critical point here. X is equal to 1. So I'll make my number line. So if I pick a number larger than 1, and by the way, if you have factored, it's always quicker and easier to substitute it into the factored form to decide whether f prime is positive or negative. So if I pick a number bigger than 1, let's say 2, I'll have 2 minus 1 is 1, times 1 is 1, f prime is positive here. And then if I pick a number less than 1, say 0, I'll have 0 minus 1 is -1, times another -1 is +1, f prime still positive. So at x equals 1, f has neither a local minimum nor a local maximum because f is differentiable but f prime does not change sign at x is equal to 1. All right. So now let's analyze the critical points and the increase-decrease behavior of f of x is equal to cosine squared x plus sine x on the open interval from 0 to pi. Well, that looks like fun. So the derivative, f prime of x, will be 2 times the cosine of x times, because of the chain rule, negative sine x plus cosine of x. So we take the derivative, and now we go, okay, is there any place where that's not defined? And since sine and cosine are defined everywhere, there's no problem there. So we'll set this equal to 0. To solve this, what we'll need to do is factor out a cosine. That would be cosine of x times negative 2 sine of x plus 1 is equal to 0. So either cosine of x is equal to 0 or negative 2 sine x plus 1 is equal to 0. On this interval, the only place where cosine is equal to 0 is at x equals pi over 2. Here, we would need sine of x to be equal to a half. And sine's equal to a half on this interval at x is equal to, let's see, pi over 6. And x is equal to 5 pi over 6. All right, so we've got lots of critical points here. I'm going to make my number line a little bigger, but I'm only going to go from 0 to pi because it specifically said on the interval from 0 to pi. Then I've got a critical point at x equals pi over 6, right in the middle at pi over 2, and over here close to pi at 5 pi over 6. On this one, it becomes a little more difficult to find test points. I'm not going to mess with this one from 0 to pi over 6 just yet, but between these two, I could use, for example, pi over 4. That's a fairly easy one. And again, substitute into the factored form is usually a little faster. So I'm going to have cosine of x, that's square root of 2 over 2, so that's positive. Again, I don't really care what its value is, I just care whether it's positive or negative. And then I'm going to have negative 2 times square root of 2 over 2, so that'll be negative square root of 2 plus 1. So if you've got negative square root of 2 plus 1, is that positive or is that negative? The square root of 2 is bigger than 1, so this is going to be negative. So I've got a positive times a negative, so here f prime is going to be negative. If I pick 3 pi over 4, which would be in this next interval. Let's see, cosine at 3 pi over 4. All right, so that's in the third quadrant now. I'm sorry, in the second quadrant. Is cosine positive or negative in the second quadrant? Yep, so that's negative. And then sine at 3 pi over 4. Well, sine in the second quadrant is positive. So that's going to be, so far we've got square root of 2 over 2 times sine in the second quadrant is positive. So this is going to be negative square root of 2 plus 1 still. Sorry. I kept thinking that was wrong. It's like, yeah, cosine is negative in the second quadrant. So I've got a negative times a negative is positive. So here, f prime greater than 0. Now, for these last two, there's really no good test point. There just isn't, right? You know, like I could do, something over 12, but then you get into half angle identities and all that kind of junk. And honestly, I want nothing to do with that. Okay? But if I think about this, if I was to, and I don't expect you to do this, but if I was to graph y equals negative 2 sine of x plus 1, what I know so far is that at pi over 6 it's going to be 0, and again at 5 pi over 6. Sine at 0 is 0, so I know that this starts off positive. So it must have started off positive and then gone negative, and then, whereas cosine in this region, so this part in this region is positive, right, from 0 to pi over 6. And cosine's also positive in this region. So this is f prime greater than 0. And then when we get over here, this expression, negative 2 sine x plus 1, is positive, but cosine is now negative because we're in the second quadrant. So this is f prime less than 0. By the way, it doesn't always switch. Like on this one, we didn't have a switch in the sign of f prime. A lot of times you do, but not every time. So, f is increasing on, I'll put it open at 0 because it said open at 0, but then to pi over 6 closed at that, and on the closed interval from pi over 2 to 5 pi over 6. And then decreasing on the other two intervals, from pi over 6 to pi over 2, and from 5 pi over 6 to pi. And I'll make it open at pi because, again, they told me open at pi. So where f prime changes from positive to negative, f changes from increasing to decreasing, so there must be a local maximum there. So f has a local maximum at x is equal to pi over 6, and then again at 5 pi over 6. And then f has a local minimum at x is equal to pi over 2. And you can, test this by looking at your calculator. You could graph this and you can kind of see, does it do these things? All right. Well, that is it for today.